3, 2.
Hello, and welcome to the School of Newton, where today we will explain Newton's laws.
For those of you that don't know, Isaac Newton was a physicist and mathematician in the 1600s. He created the laws of physics that we know today as Newton's three laws. These laws deal with the physics of how different forms of matter behave in our universe.
Newton's first law is that an object in motion will stay in motion unless an unbalanced force opposes it. An object at rest will also stay at rest unless an unbalanced force opposes it. So, you will demonstrate this with this. An object in rest will stay at rest. Seems good so far. Now let's test its motion. Newton, you liar! So you may be wondering, why didn't that work? Is Newton wrong? So find out next time on Mr. Morse's assignment.
No! Newton was right. I hate when TV shows do that. But Newton was right, because there are unbalanced forces in its path that stopped it from moving, or, in our case, with friction, slowed it down. The wall stopped it from moving because it is also another solid object. Let's see what happens if there were no unbalanced forces in its path. Now we will explain Newton's second law, which states that the amount of force can be calculated by mass times acceleration.
And, for an example, we will chuck this at this wall here, and we will calculate the force of that. Are you guys still recording? So let's calculate the force of that. To find the force of squishy, we're going to be using Newton's second law, which states that force is equal to mass times acceleration. So the first thing we're going to do is find the mass of squishy. So using our triple beam balance, we're going to calculate the mass of squishy here. So from here we know that it's less than 320 grams and less than 310. So now with this little weight, we just gradually increase in grams, and we'll see when it starts to dip. I think we found our number. Therefore, squishy is about 308 grams. So, we now know that the mass of squishy is 308 grams. But for this calculation, we're going to be putting this in kilos. So, we already know that's 308 kilograms. So, we can now rewrite the equation as force is equal to 0.308 kilos times acceleration. Now for acceleration, this one's going to be a little bit tricky, because acceleration is equal to a change in velocity over time. But velocity is equal to distance over time. So, to get it out of the way, we're going to find out how much time it takes. To calculate the change in time, we're going to replicate the throw. I'm going to throw a squishy from around where we were sitting to the door at approximately the same speed, and we're going to see just how much time it takes. So, 3, 2, 1, go! Ah!
Not again.
What was our time?
63 milliseconds.
63 minutes. Thanks, Dead Josh.
You're welcome.
Now let's find the distance.
To calculate speed, we need to find the distance between where I threw it to where my victims' faces were. So to do that, we're going to measure it. If I put this approximately where I threw it to where I hit their faces, we get a little over 7 feet, or to be exact, just under 87 inches. So the measurements we found were 0.063 seconds after calculating that 63 milliseconds is that many seconds, and approximately 87 inches. So now that we have this, it can be said that velocity is equal to 87 inches over 0.063 seconds, but for this calculation, we want this in meters per second squared. So to do that, we need to find out how many meters 87 inches is. After a quick conversion, we found out that 87 inches is actually 2.2098 meters. So, to calculate this in meters squared, all we have to do now is divide this by the seconds twice. So let's go do that. So, with our handy dandy calculator, we can put in 2.2098 divided by our seconds, which was 0.063, twice, which will give us this number. This number, in turn, is 556.764, I'll just end it there, meters per second squared. So now that we have this, we need to, this right here, this whole value is acceleration. So now, getting out our handy dandy calculator once more, we can multiply this by our mass, which, as we found previously, was 0.308 kilos. And that gives us a total force of 171.5, if I wrote that 5 right, newtons. Ta-da! So, to put that in perspective, an adult man with the force of gravity pushing down on him is about 791 newtons. So this is only like 1/5 the force of an old man getting impacted with gravity, so it's not very painful. They overreacted.
Newton's third law states that for every action there's an equal and opposite reaction. This means that if you were to push on this desk, the desk will push back on you with just as much force as you were applying to it. But as you notice, I can push it forward. That's because of the second law. The second law states that force is made up of acceleration and mass, and I am made up of more mass than this desk, therefore I push it. However, even though it's not noticeable, the desk is indeed pushing back. There's a great example of this in this video here. Oh crap! So, to demonstrate this third law, I will be slamming my hand against this table to show the equal and opposite reaction forces. Here we go. So as you can see, my hand is red because of the opposite reaction that occurred when I slammed it down. And I'm also really bleeding, like really badly. That is an expression of how much force there really was when I slammed this table, and it proves that an opposite and equal reaction does occur when you slam an object. This third law is also the reason we're even able to stand up onto this ground, because the ground is pushing back on us just as much as gravity is pushing down on it. Also, because of this opposite and equal reaction, when you jump, the entire Earth is actually pushed down just a little bit. It's not noticeable or significant at all, but if you're ever feeling not important, you can just push the Earth down. So hopefully this video has been successful in both entertaining you and educating you on Newton's 3 laws of physics. Newton is a very important aspect in both physics and engineering, as he pretty much drives the forces of everything that happens. Without him, we wouldn't be able to detect what works or not. Where are you going? What? Oh my God! It's Newton himself. Newton, wait! Come back, Newton! No, come back to me. Well, I think I'm crazy, but thank you. Thank you for watching, and I hope you learned something. Goodbye. And he created the laws which promote physics, which Isaac Newton was a move and how they do a do, basically. Well, welcome to Newton School. Explain Newton's laws. An object will also survive a deep do. Press it! You suck! Explains about the force equals gravity. No. Gravity times cake.
You can see Preston's head in the side.
Put it up a bit. Alright, Tom, I'm gonna do a funky dance. I wanna be under the ocean right now. Thomas, help me put me under the ocean. Right there. Okay. I wanna. Is that recording? Yeah, it is. Okay. That's the impact of the table. And also, you can see there's no blood happening.
Crap, we have 14 minutes.
Newton is a dude. Newton was a dude. No.
Greater than 400, so we'll bring it back to 3. 3, 2, 1, 0. No.
Did you guys say it?
Yes.
With this. I think I did it. So to do that, we're gonna use this. That one doesn't perfectly. Points, or not point. God damn. Okay, you ready? I'm sorry. Variables for speed, we can calculate it. Though we do want to change our milliseconds we calculated previously to seconds to simplify things. 1.381 milliseconds per inch. I did that backwards.